Hello everyone, this is Vikalp from Indian Institute of Technology, Kanpur. Today, I'll be presenting a work on spectral efficiency for massive MIMO multiple relay non-orthogonal multiple access systems with channel estimation errors. To begin with, let me first introduce you to the system model considered in our current work. We consider a single base station that communicates with K relays. Each of the relays is assigned a cluster of users based on the proximity between the relays and the users. The users that are associated with a particular relay are served on the principle of non-orthogonal multiple access. The communication protocol is divided into two phases, the first of which is a channel estimation phase where the K relay transmit tau-length pilot sequences which are used by the base station and the users concurrently to estimate their channels with the relays. This is followed by a two-hop data transmission phase, wherein in the first slot, the data is transmitted by the base station to each of the K relays and is then forwarded by the relays to the users in the second time slot. Let us now talk about the channel estimation phase in more detail. In the channel estimation phase, the K relays transmit tau-length pilot sequences to both the base station and the users. The base station uses these pilot sequences to estimate its links with all the K relays. Meanwhile, the users use these pilot sequences to estimate their link with the relay it is associated to. Now, in the first hop base station to relay data transmission phase, the massive MIMO base station first prepares the signals for each of the K relays. The signal for the kth relays is prepared by superposing the signal of all of the users that are associated with the kth relay according to the principle of non-orthogonal multiple access. The signal of the kth relay is now pre-coded with WK and is then transmitted to the relays. The signal received by the kth relay can be expressed as in equation 1 on the slide. Here, HK is the first hop channel, WK is the precoder, and ZRK is the additive white Gaussian noise received at the relays. The base station designs the precoder WK to mitigate the first hop multi-relay interference, and this is done using the first hop base station to relay CSI, which was estimated by the base station in the channel estimation phase. This is done on the principle of zero forcing, as shown in equation 2 and 3 on the slide. Note that since we use imperfect CSI in the calculation of zero forcing precoder, its impact would be visible in all of our SNR expressions. Next, in the second time slot, the relay forward this signal to the users. Here, the relays forward the signal to the users with a fixed gain mu k, which is given as in equation 4 on the slide. Note that mu k is a fixed gain and does not use an instantaneous CSI about either the first hop or the second hop channels and just uses the statistical values. The signal which is received at the nth user associated with kth relay is given as in equation 5. This includes some signal for all k relays because all of the users associated with all of the relays are served on the same spectral resource in the second hop. The nth user associated with the kth relays now equalizes the signal using the CSI estimated by it in the channel estimation phase. And the final received signal at the nth user associated with the kth relay is given as an equation 6 on the slide. To mitigate the intra-relay interference, the users which are associated with the particular relay perform successive interference cancellation according to the concept of NOMA. In this, the nth user associated with the kth relay first cancels the interference of all n prime users which are greater than n and treats the interference from first n minus 1 users as inherent intracluster interference. Note that for successive interference cancellation, the users require the CSI about both the first hop and the second hop channels. For the first hop channel, the user employs a statistical value of HK transpose WK, which is the first hop channel. This is as if the sub-channel of the first hop, HK transpose WK, is approximated by its statistical value, which is as in a massive MIMO system, the channel hardens as the number of antennas grows large. This is because as we increase the number of antennas, the actual value of HK transpose WK can actually be approximated by its statistical value, according to the law of large numbers. For the second hop channel, the users employs a MMAC channel estimate, which is obtained in the first channel estimation phase. Finally, the entire intracluster interference term can be given as follows. This includes an inherent intracluster interference on the left side of the equation, which is the interference from the first n minus 1 users, while a residual intracluster interference terms, which is due to imperfect SIC, arising due to using the estimated CSI and the statistical CSI of the users. We are now in a position to derive the spectral efficiency of the system. The rate expression of the nth user associated with kth relay is given as on the equation on the top of the slide. Here gamma kn is the SNR of the nth user associated with kth relay, which is given as pkn naught by summation of ikni plus 1. Here pkn naught is the desired signal term and ikni are each of the interference terms in the denominator of the SNR. IKNI1 and IKNI2 are the inherent intracluster interference and residual intracluster interference, which we just discussed. IKN3 is a second hop interrelay interference, which is because all of the K relays serve all of the users on the same spectral resource in the second hop. IKN4 is due to the imperfect CSI at the base station, which is used in designing the ZF precoder. And ICANN5 is simply the noise which was forwarded by the amplifying forward relay along with the signal. But note that the spectral efficiency, which we just saw on the previous slide, uses the instantaneous CSI of the expressions and is therefore not usable in practice. Moreover, this spectral efficiency terms contains an expectation outside the logarithm and makes it very hard to derive. We therefore resort to using a lower bound. We derive a lower bound using the use and then forget technique, wherein the channel estimates are used only to equalize the received signal, but not for actual detection of the signal. In this technique, the actual desired signal term can be split into two terms. The first one is the true desired signal, which is actually the scalar mean precoded signal of the desired term, while the signal leakage term is a deviation of the statistical value of desired signal from its actual value. Therefore, the signal leakage is actually a zero mean term, which is also uncorrelated from the true desired signal, and therefore can be treated as um, an extra Gaussian noise while calculation of the spectral efficiency. We therefore use this lower bound to derive a spectral efficiency term. The spectral efficiency lower bound is given as in this slide. The lower bound for the nth user associated with kth relay is given as an equation on the top of the slide. Note that pkn naught and ikn naught are the true desired signal and the signal leakage term. IKN1 and IKN2 are the inherent and the residual intracluster interference terms. IKN3 is the second hop intercluster interference and IKN4 is the first hop intercluster interference, which was due to the imperfect zero forcing at the base station. And IKN5 is a forwarding noise of the relays. We now derive each of these terms as follows. PK0 can be split um, by splitting the independent terms in the equation, and we can finally obtain a relatively simpler term for PK0. A similar exercise can be done for each of the interference terms to obtain a closed form expression for the spectral efficiency lower bound we just saw. We now check on the asymptotic behavior of each of these terms. The true desired signal approaches a finite value as the number of antennas tends to infinity. The signal leakage value also approaches a finite value as it turns into infinity. We note that all of these values are actually independent of the first hop CSI, which is alpha I and Ni. And therefore, as the number of antennas grow large, we can conclude that each of the signal and interference term become independent of the first hop CSI. The residual and second hop intercluster interference show similar trends. Finally, we note that the first hop intercluster interference and the relay forwarding noise vary inversely with the base station antenna and therefore become negligible asymptotically. Here, IKN4 was the term due to imperfect CSI in the first hop, which, as we just saw, since all of the terms become independent of the first top CSI, this particular term tends to zero in. And IKN5, which was the forwarding noise of the relay, approaches zero as the number of antenna grows large. This shows that the fixed gain relaying which we employ is good enough if we have a massive MIMO base station with us. The asymptotic spectral efficiency lower bound can finally be given as an equation 8 on this slide and can be used as a benchmark for our general spectral efficiency rate expression for arbitrary number of antennas. Let us now discuss the simulation results. On this slide, we have shown two plots. First is the spectral efficiency versus base station transmit power, and the second one is the spectral efficiency versus number of base station antennas. We observe that the gap between the simulated and lower bound is actually marginal, which is shown by both figure A and B. We can also see that in figure A, we have compared the performance of non-orthogonal multiple access with SDMA and TDMA systems. Here, SDMA system is spatial division for multiple access, wherein each of the K relays serve a single user at a time, while in TDMA scheme, only one user is served in one time slot. We can clearly see that SDMA is outperformed by NOMA scheme by 2 bits per second per hertz, while it outperforms uh, TDMA scheme by about 4 bits per second per hertz. In the next simulation result, we plot the pilot transmit power versus the spectral efficiency. We clearly note that for low pilot transmit powers, the advantage of non-orthogonal multiple access over SDMA is actually insignificant. But as we keep on increasing the pilot transmit power, the non-orthogonal multiple access system outperforms spatial division multiple access systems uh, drastically. This is because both the first hop and the second hop CSI are critical in the current design of our system, which are directly used in successive interference cancellation, which is a crucial aspect to reap the benefits of non-orthogonal multiple access. To conclude, we have derived the spectral efficiency for a multiple relay-aided massive MIMO NOMA system with finite number of base stations. We have then compared the spectral efficiency of the multiple relay-aided massive MIMO NOMA system with conventional NOMA schemes such as SDMA and TDMA, and we have shown that the massive MIMO NOMA system requires accurate channel estimation to outperform NOMA or orthogonal multiple access schemes significantly. Thank you and have a great day.